So thank you again for introducing me and being part of this workshop. In this session, I will present the green heat module, which was mentioned earlier. Starting from this. No. Second. How can I change slides? Okay. Okay. So in this presentation, I will start with the purpose of the green heat module, and also relating to the title of the session, energy efficiency through renewable energy sources. From that on, I will also present our experience, so the experience of Kraftanlagen in this technology field. I will show you the basic functionality of the technology. Do a short comparison to other solutions, and then summarize the benefits that we see in the application of this technology. So the first step, tackling the efficiency point, would be that I would like to make a short comparison here. Mr. Panousis already mentioned in his presentation that the district heating technology by itself offers a significant increase in efficiency in the use of fuels. So if we look at an example calculation for a residential load profile, usually there's an electricity demand, and then there's also a heat demand, which is usually of the magnitude 2 to 3 times higher than the electricity demand that we have. So state of the art for many years, and also still in many regions over the world, is the separate generation of power and heat from fossil fuels. So there's one way. We have local heat provision from inside each household, burning mostly natural gas. You see this as the first example. And separate to this, we have traditionally big power plants burning also fossil fuels like coal, gas or oil, producing high pressure and high temperature steam, converting these in turbines to electricity, and then supplying it via the grid to the customers. So on the electricity side, we have here the lack that this technology is limited in efficiency. So modern steam cycles are limited to about 40 to maybe 42% of efficiency on the electrical side. So which on the other hand means that around 60% or even more of the fuel put in is lost through cooling to ambient, so it's not used anymore. So the first step, and this is basically state of the art, is switching to combined heat and power. So not having each household generating its heat locally, but instead using the waste heat from the power plants through cogeneration or CHP, combined heat and power generation. And just by doing so, we have a small lowering in the electrical efficiency of the power plants, but an overall increase in efficiency to about 90% most of the time. So in total, just by doing so, we can save about 30% of the energy that is needed to provide the heat and power. So the next step would be now the thought: what if we want to replace the fossil fuels through renewable energies? So in most cases, this just starts by installing a generation capacity of solar power and of wind power, for example. I would like to ignore at this point other sources like hydropower, biomass power, and so on, as in the end their potential is quite limited, and I think the vast majority of renewable energy potential is solar and wind power, which we can exploit at the moment. And we have also come to a point right now where the generation price of solar and wind electricity is already comparable to the price of the fossil fuels we are burning in the thermal stations right now. So we are now in a competitive range, but we have two problems here. If we just say, okay, we install more renewable capacities. One is the fluctuating generation of the renewable energy sources. So we are having on the right side an electricity demand, which is largely not controlled yet. The consumers are used to get electricity when they want it. So we have a mismatch here between generation and demand. And the other thing is that by just installing renewable electricity generation capacity, we are ignoring, let's say, the elephant in the room, which is invisible in most discussions, which is the heating demand, which is in most cases just still supplied by fossil fuels. So to address these two issues, we need storage. So basically there are two technologies. If we want to replace the fossil fuels completely, we would, at first point, we need to do power to heat, so converting the renewable electricity also to the heat sector to address this demand, and also to address the fluctuating generation, we have to store the energy. So the first thing that comes to mind when hearing energy storage is, for most people, the battery. But unfortunately, storing the energy on the electricity side is very expensive. So battery capacity is still very expensive and is only utilized in quite low scale due to this, and also for only shorter periods of time, in the range of several hours of storage capacity. But anyhow, to utilize and unleash the full potential of the renewable energy, it is mandatory to store it. So that's where our technology approach comes into play, what we labeled as the green heat module, which is basically a high temperature thermal storage with an electrical heater. And the key would be to change this generation profile to this and reuse the formerly used thermal path of energy provision by using the renewable electricity when it's available and the demand is there directly. But when the demand and the production is mismatching, we are taking the surplus renewable electricity, converting it into high temperature heat and storing it for the later use. By doing so, we can drastically reduce the cost of the energy storage, because storing thermal energy is way cheaper than storing electric energy. And then afterwards, when we need it again, we can use the stored high temperature thermal energy to run a thermodynamic cycle, for example, a combined heat and power steam turbine cycle, converting it back to electricity when solar and wind is not needed, and as a side effect, providing the heat from the cycle to, for example, district heating networks. And by this, we are in principle able to replace the fossil fuels in a combined heat and power application. So the green heat module itself is basically the core component which has been developed by Kraftanlagen, the technology, for about 15 years now. Basically, what it does, it converts intermittent production renewable energy sources via electric heaters to heat at temperature ranges between 750 and up to 1000 degrees Celsius. This is actually tested in the multi-test facility that we built up together with the Solar Institute in Jülich. Then we can store it over hours or days, and then afterwards we can use it with a very high efficiency to drive a thermodynamic cycle and provide either high temperature process heat or via a CHP application, re-electrify it, and as a side effect provide district heating, for example. And due to the generation prices of the renewables that we see today, we see that this can be done nowadays to a price which is comparable to natural gas, for example. So this is also an economically feasible alternative to fossil fuels nowadays. So our experience on this field, I would shortly give an overview here. As I said, we are on this field as a company for over 15 years now. It started in 2006, where Kraftanlagen gained, together with the research partners, the Solar Institute and the German Aerospace Center (DLR), gained experience in the detailed design for thermal storage and also solar thermal solar thermal power generation. Then in 2009, Kraftanlagen was the main contractor for the building of the Jülich solar tower power plant, which at first as a first plant utilized in large scale with a capacity of 20 megawatt hours the thermal storage system that is also the base for the green heat module technologies nowadays. And then 2015 we started to do a new design and take this storage technology which was developed for the solar thermal technology and basically make a standalone storage plant out of it, which was then constructed and is in operation since 2021, also at the research campus of the Solar Institute in Jülich now. So what is the base principle of the green heat module? So the core elements is a high temperature heater and a ceramic storage material. What the system does is when we have renewable electricity available, or what can also be used is, for example, surplus electricity from a grid. We've already heard that in Greece there is already in many regions the problem that renewable electricity cannot be generated because the electricity grid is basically fat, so they have to turn down. So the system could also use this electricity, which would otherwise not be generated, and convert it to high temperature heat. The electric heater is then heating up a flow of ambient air to temperatures up to 1000 degrees Celsius. This hot air is then driven through the ceramic storage material, storing the heat in the solid material, and afterwards recirculated by blowers to the heater, and the cycle starts again. When the renewable renewable sources are not producing, or for example there is the need for power in the system, or also for heat generation, then we can take the stored high temperature heat, drive an airflow through the ceramic storage material, heat it up again to a temperature nearly as high as the initial temperature where the heat was generated. Then run it through a heat exchanger, run basically any thermodynamic cycle with this heat, and afterwards recirculating the air to the storage material, heating it up again. What the system also could incorporate would be an optional fuel burner. So for situations when the thermal storage is empty and there is no electricity available, for security of supply reasons, there can be integrated a burner, for example, burning natural gas or biogas, or in the future we can think about hydrogen or ammonia, any basically renewable generated fuel that could be available in the future to secure the supply, even when the storage is not charged by renewable electricity. Sorry, wrong button. Just shortly, because this question is very often asked to us, I want to address this in advance in this session. Why we are using ceramic storage material? Because this is a material that has to be manufactured, it has to be processed, and is therefore, compared to some other alternatives that are proposed on the market, let's say it's more expensive as it is an artificial material, but in comparison, for example, to having a packed bed storage with just natural stones or sand, which is proposed by also some concepts in research, it has one great advantage, because in practice, when you're building a big heat storage, the statics of the building is a very important factor, and this ceramic material incorporates this. It has basically both functions. It stores energy, and it is self-sufficient, so it does not need any support structure. It's like bricks that you can use to build a house. So it's self-supporting, eliminating many technical problems, and also what it incorporates is a very good, basically a temperature profile. Due to the defined heat transfer surface, we can have a very moderate drop in temperature that we have from generating the heat with the electric heater to after using the heat to drive a power cycle, which is very important in the power plant application. So a short summary of my key facts that I want to give in this presentation. So the first one is this energy storage is the key to unleash the potential for renewable energy and have a high penetration of renewable energy in both electricity and heat sectors. The second is that the decarbonization of the heat sector is equally as important as the decarbonization of the electricity sector, and in the end this can only be achieved, according to our opinion, by linking both sectors and using synergies between both of them. And the green heat module can just do that, coupling both sectors, storing the energy, and providing back heat and electricity, therefore acting basically as a battery and in parallel as a renewable heating system. And the last point is due to the long year research work and demonstration work, this technology is today proven, and we can say this storage technology is reliable and ready for application. So, thank you everyone, and looking forward to discussions afterwards.